In this session of CCNA series, I'll discuss how spanning tree protocol works. STP or spanning tree protocol is a protocol that builds a loop-free logical topology for layer 2 networks. STP uses spanning tree algorithm to create a topology database of the network. And to prevent loops, STP places some interfaces in forwarding state and other interfaces in blocking state. It does this based on three criteria. First, it elects a root switch and puts all the working interfaces on the root switch in forwarding state. Second, all other non-root switches determine the shortest path to get to the root switch. Third, on the shared Ethernet segment, switch with the lowest root cost or best path to reach the root switch is placed in forwarding state. You can call this switch as a designated switch, and its interface is called designated port. All other interfaces are placed in blocking state and will not forward frames. The above functions and many more are performed by exchanging BPDUs, also known as Bridge Protocol Data Units. BPDUs are messages used by switches to exchange STP information with each other in order to elect a root switch and detect loops. The most common messages are called hello BPDUs. Let's go ahead and look at the first criteria, electing the root switch. The first step of the STP process is to elect the root switch in the network. The election is totally based on the bridge IDs sent in the BPDUs. The switch with the lowest bridge ID is chosen as the STP root switch. The bridge ID is 8 bytes and consists of 2-byte priority field and 6-byte system ID, which is nothing but a universal burden MAC address on each switch. The MAC address and priority together make up the bridge ID. Bridge ID or BID uniquely identifies every switch on the spanning tree. For example, if switch 1 has a priority of 4096 and MAC address of AAA, and the other switches have a priority of 8192 and a MAC address of triple B and triple C accordingly. The switch with the priority 4096 will win the election, regardless of what MAC address are used to create the bridge ID for each switch. In case of tie, in priority, the switch with the lowest MAC address portion of the bridge ID is the root. Here you can see switch 1 becomes root switch after comparing bridge ID from each switch in the LAN. Let's look at the second criteria, choosing each switch's root port. The second part of the STP process is for every non-root switch to choose its one and only root port. A root port or RP is a port that has the best path or least STP cost to reach the root switch. Of course, a root switch has the best path to itself, so it will actually have no root ports. Every other switch has only one root port. So let's take a topology where switch 3 has two possible physical paths to forward the frame to the root switch. The direct path to the right and the indirect path to the left through switch 2. As you can see, the cost over the direct path out of switch 3 GI01 port has a total cost of 4, and the other path has a total cost of 4 plus 4, that is 8. So switch 3 picks its GI01 as root port, as it has least cost path to send frames to the root switch. And similarly, switch 2 chooses GI01 as its root port. In case the costs are same, and if a tie occurs, the switch applies these three tie breakers in order as follows. The first one is choose based on lowest neighbor ID, neighbor bridge ID. The second one, choose based on lowest neighbor port priority. And the third one, choose based on lowest neighbor internal port number. Next, let's look at the third criteria, that is choosing the designated port on each LAN segment. STP final step to choose the designated port on STP's final step is to choose the designated port on each LAN segment. So what is the designated port and how to choose the designated port on each segment? Well, designated ports are the ports facing downstream away from the root switch. And that is the reason the root switch has designated ports only. A designated port is in charge of sending and receiving traffic on a segment shared by two or more non-root bridges. The switch with the lower cost to reach the root among all switches connected to a segment becomes the DP on that segment. You can call this switch as a designated switch and its interface is called designated port. And all other interfaces are placed in blocking state and will not forward frames. Can we influence the STP topology? Yes. Switches have default bridge ID and based on default priority value and MAC address. In order to influence the STP election, there are two options available. First one, you can change the bridge ID. For instance, giving a switch the lowest priority value among all switches will cause that switch to win the root election. Second, change the STP port costs. For instance, to favor one link, give the port on that link a lower cost, or to avoid that link, give a port a higher cost. Let's go ahead and look at the STP timers. STP timers can manage the STP convergence. Okay, STP is controlled by three different timers, and the convergence process requires the use of these three timers. The first one is hello timer. Time period between two consecutive hello BPDUs created by root switch. And hello BPDUs are sent every 2 seconds. Then we have max H timer. The max H timer controls the maximum length of time that passes before a bridge port saves its configuration BPDU information. So a switch would go 20 seconds without hearing a hello before reacting. Then we have forward delay timer. Forward delay is the time that the switch spends in the listening and learning states when it's transitioned from blocking state to forwarding state. A port stays in an interim listening state and then an interim learning state for the number of seconds defined by the forward delay timer. That is 15 seconds in the listening state and the 15 second in the learning state. Let's go ahead and look at the STP port states. In case if you have observed on Cisco switches, when you plug in any device on an interface of the switch, it transitions from orange to green, during which it goes through a series of spanning tree port states, or when a port that was formerly blocked due to spanning tree needs to transition to forwarding, it transitions through different states. STP states are as follows, starting with disabled state. In this state, it has both its physical and logical lines down. In regards to Cisco, this would be a down or administratively down interface. A port in disabled state does not process BPDUs or it does not forward any user traffic. Then we have another state, that is listening state. This is a transitional state. Okay. In listening state, spanning tree calculation starts. The port can send and receive BPDUs but does not forward any user traffic. And by default, the port spends 15 seconds in this state. Next, we have learning state. This is also a transitional state. In this state, a loop-free MAC address forwarding table is established, and the port does not forward any user traffic. By default, the port spends 15 seconds in this state. Then we have forwarding state. A port in forwarding state can forward user traffic and process BPDUs. Only the root and designated port can enter the forwarding state. Then we have blocking state. When a port is neither a root or designated port, it will be in blocking state. A port in blocking state receives and processes only BPDUs, but it does not forward any user traffic. So let's go ahead and see how STP state transitions take place. So when a port is enabled, STP moves an interface from blocking to listening if the forward delay timer expires. The port transitions to the learning state, and again after the forward delay timer expires, it transitions to the forwarding state. STP leaves the interface in each interim state for a time equal to the forward delay timer, which defaults to 15 seconds. And as a result, a conversion event that causes an interface to change from blocking to forwarding requires 30 seconds to transition from blocking to forwarding. In addition, a switch might have to wait max age timer, that is default 20 seconds, before even choosing to move an interface from blocking to forwarding. And if the interface is not a root port or a designated port, the port enters the blocking state. I hope this was informative for you. Thank you for watching.